What is going on, guys? Welcome back. In this video today we're going to implement Gaussian elimination from scratch in Python, which is an algorithm for solving systems of linear equations, and implementing it from scratch can help you understand it better. So let us get right into it. Alright, so we're going to implement Gaussian elimination from scratch in Python today, and the main purpose behind this is to understand the algorithm better. It's not because we need it, we can just use the linear algebra module from NumPy if we want a solution to a system of linear equations. The main purpose is to better understand Gaussian elimination by coding it out, by implementing the individual steps. And we're going to do that in this video today. Now, just as a quick recap, I'm not going to teach you Gaussian elimination in general, but for those of you who maybe learned about this some time ago, just a very brief reminder for what Gaussian elimination is. I'm going to open up my paint here briefly. The basic idea is we have a system of equations, something like 3x plus 2y minus z is equal to 5. And then we have something like 2x plus y minus 3z equals 2 or something, and we take such a system, maybe we have a third one here to make it complete, 4x minus 2z equals 1 or something like this, and we take this and turn it into a matrix. So we have 3, 2, -1, 5 into an augmented matrix here, 2, y, -3, or sorry, not y, 2, 1, -3, 2, 4, 0, -2, 1. And the Gaussian elimination now basically is we can swap rows, we can add equations, and we can multiply with scalars. And the goal is to get to the so-called reduced row echelon form, where we have ones here and we have zeros here. And then we can just substitute back the solutions, and we get, or we can do the substitution, and then we can get the results for x, y, and z. That's the very basic idea. I'm going to maybe sketch it out again when we get to the individual sections, but we're going to implement this from scratch in Python now. So what we're going to use for this is we're going to use NumPy, but we're not going to use linear algebra from NumPy. So we're just going to use NumPy to work with arrays, not in order to solve the or to do the algorithm for us. So I'm going to open up a new file now. Let's go to my current directory. Let's remove everything that's in here. And then let's create a main py file, which we're going to just delete the swap file here. So I'm going to zoom in. And what I want to do first is I want to have a NumPy-based, or a linear algebra NumPy-based function that can give me the correct result, so I can double check if I'm doing everything right. So I'm going to say import NumPy as np. And then we're going to define the function solve system of equations, and we're going to get a and b as input here, a being the matrix representing the coefficients, and b being the target vector or results vector. And we're going to just say now try to get a solution by saying NumPy linear algebra solve a and b, and then we can just return the solution. And if we get the exception that is the NumPy linear algebra linalg error, so linear algebra error, if we get that, we return system has no unique solution. So that is going to be our method that we use, or our function that we use to double check if something is done correctly or not. We're going to use a simple example here first. I'm going to define an array, and this array now is going to contain our individual rows. So we're going to say here 3, -1, -1. That is equal to saying 3 times x minus 1 times y minus 1 times z is equal to whatever is in b at that position. Then I'm going to say, come on, then I'm going to say 1, 1, 0. I need to do something about this auto-completion. And then we have 2, 0, -3. All right, so this is our coefficient matrix, and then our results vector is going to be np array, and it's going to just be 5, 0, 2. So these are our equations, 3 or 3x minus y minus z is equal to 5, x plus y is equal to 0, and x minus 3z is equal to 2. And we're going to try to solve this system of equations now. Now I can do this right away with my function here. So just a and b will give me the correct answer. And this is what we're going to compare our solution with. So 1.3, negative 1.3, 0.2. All right. So let's solve this with Gaussian elimination implemented from scratch. And for this, I'm going to go ahead and say Gaussian elimination, AB. Actually, Gaussian elimination is only the process of getting it into the reduced row echelon form. We can then also do the substitution, which is, I think, not part of the Gaussian elimination. I might be wrong about this, but we're going to do both. We're going to basically solve the system. So what we're going to do first is we're going to create the augmented matrix. So I'm going to say n is equal, first of all, to the length of A to get the dimensions. And then I'm going to say augmented is equal to np. And then we're going to use the column stack function to just concatenate the columns of A and B. So we get this augmented matrix with this line in between, even though, of course, there is no line. This is just some notation for humans. And then we're going to turn this into a float matrix. So this is our augmented matrix, and now we're going to just perform the basic operation. So what we want to do is we want to take the rows that have the highest pivot element, and we want to swap the rows if necessary, so that the row with the highest value for that pivot column that we're currently looking at is at the current position. So maybe this was not the best way to phrase it. Let me show you visually what I mean by this. If we have some, I'm not going to choose the one that we have now, but if I have some matrix that has maybe a value 1, 2, 3 in here, and then also the other values here, whatever they are. And then I have maybe some 3, 2, 2, and then maybe I have 5, 1, 1. Then the goal is to get the highest pivot element, the highest value here at this position. So this is the pivot element, and we want to have the highest value here. So we would swap these two rows. Then for the second column, for the second column, we want to have the highest pivot element in this position. So if this was, for example, 3, we would swap it so that the 3 is at this position. We want to have the highest value always at the pivot position, so to say. So we're going to do it the following way. We're going to say for I in range n, which is the dimensions of our matrix, we're going to say that the pivot row by default is going to be just the first row. And then we're going to say the maximum value at the position that we're interested in right now is just going to be that specific the value that we have. So it's going to be the absolute value. But by the way, maximum means absolute maximum value. So maximum absolute value. We're not interested in positive values, only want to have the highest absolute number there. So maximum value is equal to absolute value of augmented, and then we're going to take the diagonal element. In the first iteration, it's going to be the first one, then the second one, and so on. It's always the diagonal. And then we look for the highest value. So we say for k in range I plus 1, because I don't need to consider myself. I don't need to consider the first row up until n. And we're going to say if the absolute value of the element in this row, so if augmented k, still I, because we're looking for the first column, then the second column, then the third column, if that is larger than the max value, we're going to say that the max value is equal to that augmented matrix ki value. So that would be, if I use the example here again, it would be this value here. So I would say this is augmented II, so 1, 1, or actually 0, 0 in the first iteration. And then we would say, okay, this one is higher, so now that would be my choice. But then this one is even higher, so that would be my choice. So I basically keep track of the highest value, which at the end would be 5. And I say that the pivot row is going to be k every time I find a new value. So that is now my pivot row. And once I'm done with all the rows, so I definitely found the best one, what I'm going to do is I'm going to say if the pivot row did not remain the same, so if it's not equal to I, I'm just going to swap the rows. So I'm going to say augmented I is going to be equal, or augmented I, augmented pivot row, whatever it is, it's just going to be swapped. So we're going to say augmented pivot row, and I'm going to use a copy here, and augmented I copy. So we're just swapping the columns. So since this is the best, since this is the highest value for the first column, this is my pivot row, so I perform this swap. So these two are now exchanged, including, of course, these values. So that is that, and we're then going to check if this value, it's the best one, so we don't have to check for all the values, but if this best value, if this maximum value is close to 0, I'm going to say that the system has no solution, because that is then basically problematic, because if it's 0 or very close to 0, we cannot work with this. So I'm going to say if the absolute value of augmented II after the swap, so of my pivot element, which is the optimal one, the largest one, if that is below a certain threshold, let's say 1e negative 10, which is very small, I'm going to return system has no unique solution. All right, and otherwise I'm going to just continue. I'm going to say that that the pivot is equal to augmented II. So this is now, in this case, we would swap the rows, and then this one would be here. So I would have, maybe actually let's do this to not keep this too abstract. So I'm going to delete 511, and then here we had 133, I think. So 511, 133, and then we would have 15, and here we would delete the 1. So that would be the swap, and then that would be my pivot element. So I would say augmented II is the pivot, and then I would say I want to divide this row by the pivot element. So augmented II shall become whatever it was before, or actually the whole row, sorry, not just the pivot element. The row should be whatever it was before divided by 5. So basically we're taking all these values here and replacing them. So this becomes 1, this becomes 1 over 5, this becomes 1 over 5, this becomes 3, and so on. So we do this to get the reduced row echelon form where we have the 1s at the diagonals. So we want to have 1, 1, 1 here. So this is why we do that. We do this division, and then we do the following. We eliminate the pivot element from the rows below. So remember, row echelon form, reduced row echelon form means 1, 1, 1, but it also means that these here have to be 0. So we need to eliminate the 3 and the 1. So what we do is we say for j in range I plus 1 to only consider the rows below. What we do is we say, give me the factor. The factor is just the number that I have here. So this is 1. So I only need to take this as many times as I have here. So in order to eliminate this element here, I just have to take this row minus that many times this row, because I have a 1 here. So in this case, this row here minus 3 times this row here will result in this becoming a 0, because 3 minus 3 is 0. So factor is going to be the augmented ji, the first element, or the element in the same column but in all the other rows. That's going to be the factor, and then I just say augmented j is going to be equal to augmented j minus the factor times augmented I, which is of course valid. We can add, we can swap, and we can multiply with scalars. Multiplication also means division. Adding also means subtracting. So we can just do this, and then we have the zeros below our pivot element. And this, of course, is repeated now for all the different columns. That thing that we just did here is repeated for, is done once for this. So after being done with that, we're going to have a 0 here, and whatever we get when we take this minus 3 times that. So we're going to have some other value here and here and here. And then we're continuing with this. So we're trying to find the pivot element or the row with the largest pivot element in this position. It's going to be that. So we swap these two rows, and then we perform the same operations again and again until we have all the rows handled. And that's actually it. That is already now our matrix in reduced row echelon form. So we already have the form done. The only thing that we need to do now to get the solution is we need to substitute back. So we need to say, is this a proper indentation? We need to say x is equal to np zeros and size n. And then we just say for I in range. And think about it. What do we need to do? I'm going to use now a different example. What do we need to do if I have a matrix that is already in reduced row echelon form? So if I have 1, 1, actually let's make this like this, 1, 1, 1. Then I have zeros here, and then maybe I have something like 2 and 3 and 2, or let's maybe say 1. And then I have some values here like 10, 5, 15, whatever it is. This is not our example now, but if I have this reduced row echelon form, what do I need to do? Well, in order to get one of the variables, I just need to get this one here, and that's going to be equal to that. So I know that z is equal to 15. Then I need to get this one here and subtract the value from the other row. So I need to take this, but I also need to subtract 1 times this value. So let me put this into code and then explain it again. For I in range, we're starting at n minus 1. And we're going until -1, which means we're going until 0, but we need to say -1 because otherwise it's not included. We go a step size of -1, so we go from last row up to the previous rows, and we say that xi is going to be equal to, and then augmented, and we want to have the last element of this row. So we're taking whatever row we're at, we're taking the last element, which is, of course, this always, so that's the value. But in order to get to that value in the last row, we need to do nothing. So by doing this for the last row, we're already done. But for the other rows, we need to make sure that we actually subtract all the stuff that's still here. So we need to get rid of all this. So in order to say what y is, we need to say, okay, y is basically 5, but not exactly 5, because we need to subtract 1 times 15 from here to know what y actually is. So we say for all the other rows below, for j in range I plus 1 until the end. So for all the rows that come below the row I'm currently looking at, we're going to say that we need to subtract from our value that we took the value for that specific column times whatever that value was. So xj in this case, if we're already in this row, we would say whatever augmented ij is, so 1, times whatever xj is, and j is the one from before, so j would be 15. So I would say it's 5 minus 15. And that's basically it. Once we're done with that, we have solved the system of linear equations. I hope I didn't make any mistakes, but actually now if I run this, I should get the same result. I don't, because column stack, I need to use a list, right? Or a tuple. Okay, we made some mistake. Why is that? Let me just double check what I messed up here. So that is correct. That is correct. That is correct. Pivot row I. That should be fine. That is fine. Oh. That's the problem. I hard-coded 5. Why did I hard-code 5? Of course, it's the pivot, whatever the pivot is. There you go. Now it works. So this is how you do Gaussian elimination. Now, again, the goal of this video is not to explain Gaussian elimination in general, but to just briefly recap the code, we create the augmented matrix by combining the columns. We go through all the rows. We try to always pick the maximum value for the pivot element. We basically swap the rows so that the maximum element is always at the position of the pivot element. And then we divide by that number to make it a 1. And then we subtract from all the rows below this row to make all the values below the pivot element 0. And then what we do is we just, basically that's it. And then we just substitute back in. We take the last value, which is trivial because it's already written there. And then we take the ones above, but we subtract the values that are not 0 in this row. And then we get the solution. That's how simple it is. And to show you that this works also for larger matrices, I have another example here that we can run. I'm going to replace this one. This is a larger example. I can run this and you can see we get the same result. So we implemented Gaussian elimination from scratch. So that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video and bye.